Let me start by saying that contrary to the commonly stated opinion, LinuxCNC does not particularly recommend the parallel port as an interface. There are many much more capable alternatives. But if you are using the parallel port, then one of the obvious drawbacks is that there are not very many pins. However, in the case of a lathe, the spindle only turns in one direction during a single point threading cycle, so it just needs spindle position information and an index. This is the same requirements as an automotive crank position sensor, and the car industry hates to use more than the absolute minimum of wires, so they frequently use a scheme where a toothed wheel or magnetic target with one or more missing teeth is used. This allows the system to get position and TDC information using only one sense wire. When crank position sensors were first introduced, the target wheel was quite often the starter ring gear, with one tooth cut down to be a little shorter. This is very much a scheme that could work using a lathe spindle gear. The capability of using this scheme has recently been added to the LinuxCNC software encoder component. The setup here is a magnetic crank encoder from a Peugeot engine, and a single hall sensor wired to the parallel port with a 1K pull-up resistor on the output. 5V power is derived from the PC USB. Some very cheap ones of a different design can be found by searching for Ford part number 1256491, or search the web for a trigger ring. A secondary advantage of using a crankshaft encoder is that they have very large through bores. The hub of this one could be removed to leave a 70mm bore, big enough for even quite a large lathe spindle. This is my test setup being trialled using the LinuxCNC HAL scope. The current spindle speed in RPM is being displayed with the HAL meter, and a SIM pin has been added to set the encoder index enable input. As can be seen, the index enable goes true as I press the button, simultaneously starting the HAL scope. The pin then goes false at the two-tooth gap in the pulse train. Also visible in this trace is the problem with the single pulse scheme. Noise immunity is relatively poor, and there is a noise spike in the velocity trace. Some filtering and shielding would have been wise. The motor is being driven by an STMBL. Let's try some more speed by adjusting the current in servo term. The pulse train is obviously much faster here, but the tooth gap can still be seen, and again the index enable is reset at the gap. Winding it up to 2 amps and 1600 RPM, and it still seems to be working reliably with a 60 tooth wheel and a 50 microsecond base thread. Zooming in, the pulse gaps can be seen, and the reset is working. Currently, this function is only available in the LinuxCNC development branch, but pre-compiled binaries are available from the LinuxCNC build bot.